This problem gives us an introduction to projectiles that start with an initial launch angle. So while we don't have a difference in the height, this person, the pink person, is going to throw the football, and it's going to be launched at an angle of a velocity of 10 degrees. Let's try that again. A velocity of 10 meters per second and an angle of 30 degrees above the horizontal, and it will be caught right along that same horizontal line. So it's going to be thrown and caught at the same height. That's one thing that we can do to make this problem a little bit easier, while still giving the general feel for how a projectile problem works when it's being launched at an angle. A couple of important points to bear in mind is that, once again, the vertical velocity is under the influence of gravity. So however fast it's going upwards initially, it will be changed around and eventually directed downwards because of the acceleration due to gravity, whereas the horizontal velocity will remain constant the whole time due to the lack of external forces in the horizontal direction. And as I said before, we typically ignore air resistance in cases like this. So a couple of things to just draw your attention to right off the bat. You'll notice that I have a velocity here, and it's sort of a weird velocity. I call it the fancy pants velocity. It's just a little bit spruced up compared to your normal v. And it's sometimes also called the global velocity. It's just the overall velocity of the object, without regard to whether it's horizontal or vertical or something in between. And this angle would also be called the global angle. And if we're being absolutely precise about it, we should put a knot there, because it will be changing as the projectile follows its course to the blue person. And so our task here is to find out how far away must the blue person be standing in order to catch the football at the same height as it's thrown. One of the first things we need to do is take this velocity and split it into its component parts. So I'm just going to blow it up a little bit here. So this is 10. And this is 30 degrees. So the overall initial velocity is 10 meters per second. That's 30 degrees. And we need to get the horizontal velocity and the vertical velocity from this. So we want to make sure that we split things up appropriately. Absolutely crucial that we don't try to use 10 meters per second in the horizontal direction or 10 meters per second in the vertical direction, because it's not 10 meters per second horizontally, and it's not 10 meters per second vertically. So we'll just set up our normal givens, start off at 0, end up at some unknown position. The velocity in the x will remain unchanged the entire time. We're not going to be mixing and matching it around. There's no acceleration, there's no external torque or force. So we should just be able to keep the velocity the same the whole time. The question is, what is that velocity? It's just going to be the overall initial velocity times the cosine of the angle above the horizontal. That gives us this right here, the cosine of the adjacent side. And if I want to, I can plug in 10 meters per second times the cosine of 30, and that gives us about 8.7. We'll round a little bit right now, about 8.7 meters per second. The other thing that we can look at is in the vertical direction. Actually, not quite done with the horizontal. We don't know the time. The time is something that's relevant. How long is it in the air? How long is it moving at 8.7 meters per second? Will really determine how far away you need to be standing to catch the ball. The longer the ball is in the air, the further back you're going to be. Because the angle is pretty low, 30 degrees, we wouldn't necessarily expect this to be in the air for a real long amount of time. And that's not the same color. I'll try this one. So in the vertical direction, it starts off looking pretty boring, actually, because the initial and final positions are both 0. The initial velocity in the y direction is going to be constructed in a very similar way. And I would tend, if you don't know what the initial velocity is or the initial angle, don't just leave this as v naught in the y and v in the x. Actually plug in v naught cosine theta and v naught sine theta, because you might be able to do something with one of them in terms of the other. And these two relate together very nicely if you have substituted in the appropriate things. So this initial velocity in the y is going to be 5. The final velocity in the y, due to the symmetry of it, is going to be negative 5 meters per second. The acceleration is negative 9.8 meters per second squared, and the time we don't know. So really the only thing that we don't know, and this is kind of an overabundance of riches in terms of knowledge, the only thing we don't know in the vertical direction is the time. It just so happens we also don't know the time horizontally, since time is direction independent. And we don't know how far, and this is our ultimate goal. How far does the person have to stand in order to catch the football? So we're going to start off by looking in the vertical direction, because if I can get this velocity in the vertical direction, I can just take it and plug it in over there, and then I can easily solve for how far away the person needs to be standing. So we'll start off looking in the vertical direction. We'll take the easiest way would be to ignore these. They're just 0. They're going to cancel out anyway. And we'll do acceleration equals the change in the velocity divided by the time. Well, change in velocity is the final minus the initial. So in this case, we would be right to assume that that change in velocity is going to be negative 10. I'm going to do it in a slightly less straightforward way. So I'm going to plug in negative g for the acceleration, negative 9.8, equals negative 2 v naught sine of the angle divided by the time. Now where did this come from? Well, 1 by itself, the initial velocity by itself, is v naught sine theta. The final one would be the opposite of v naught sine theta. If I take the final minus the initial, I get 2 times the final. And that's the end of that story. So then we just solve, rearrange and solve for time. And these negatives will cancel out for us. So we end up with 2v naught sine theta divided by g. The next step then is to look in the horizontal direction. So in the horizontal direction, I just do velocity in the x equals change in position over time. And we're solving for the change in position, so I have x equals the velocity in the x times the time. We'll do a couple of substitutions here, so I have v naught cosine theta for the velocity in the x times the time, which would be 2 v naught sine theta divided by g. Now what we can do here is a little bit of fancy math. This is going to give me 2 times sine theta cosine theta, which is the same as sine of 2 theta. And I have a v and a v, so I'm going to end up with v naught squared so x equals v naught squared sine 2 theta divided by g. And once we plug in all of the numbers, what we will get is that this the person who wants to catch the base or the football will have to stand about 9 meters away, 8.84 meters. And that's about it.